So I believe we can start. So hello everyone. Again, we're glad to see you all here. I am Rashad Ahmedov from SPE BHOS school team. And thank you all for joining us. Today we are honored by Kamal Fatalizada, Process and Process Safety Engineer for BP. And last week he talked about, shared his knowledge on hazard identification techniques. And today we'll be learning from him on consequence modeling. Thanks all, and I'm leaving the stage for Kamal Bey.
Yeah, thanks, Rashad. I guess you can hear me well and you can see my presentation.
Yes.
Yeah.
All.
Okay. And thanks for joining. So as Rashad mentioned, last week we talked about hazard identification and we overviewed certain techniques like Hazid, Swift, HAZOP, FMEA, etc. So we will look at the from the risk management perspective. So if you see the overall risk management process we mentioned last week. So we said that everything starts with hazard identification, and we spent some quality time last week talking about hazard identification techniques. And this week we will build on that. So once we identified all of our hazards, so what does it mean in terms of the risk? So today we will just focus on the one of the aspect of the risk, which is consequence modeling. So as you may remember, we said that once you identify your hazard, so to be able to identify what's your risk, you should know your consequence and likelihood of event happening. And today, within risk management process framework, we will talk about consequence analysis. So how we are doing, how we should do consequence modeling, what are the techniques available, what are the mathematical, empirical, or computational models available to carry out consequence modeling. And when we say consequence effect modeling, so today I'm planning to cover what's the event itself. So we will define the event type, and we will define the magnitude and duration of the event, how we can define the magnitude and the duration of the event, and how we will do modeling versus the location itself. And if we have time, we may talk on about the evaluating impact on the target as well. When I say target, it's about the people, it's about the building, it's about the plant, environmental, etc. But let's first define what does consequence modeling mean, and what's the how we define the event, how we determine the magnitude, how we determine the duration, and what's the model effect versus location. So then we can be able to talk about the impact on the target. So, I mean, as a reference, you can find, so there is an oil and gas producer group, which is known as an OGP in the industry. And they have got like they produce series of the report. And one of their report is on the consequence modeling, which is OGP report 7. And they define actually a flow chart for the consequence modeling. So what they say that, and so you have got some hazardous substance, and we discussed last week what does hazard mean. It could be a thing, it could be a situation, it could be a condition. And from this hazardous substance, you can have like a pressurized leak, unpressurized leak, or other incident. And we will talk about later what does it mean, other incidents. And when you have got pressurized leak, obviously you will have discharge. And this discharge could be a gas phase, two-phase, or liquid. And if you have got unpressurized leak, it will form liquid pool. And we will discuss this in details, but I'm just trying to give you a brief, very light overview of the how process actually work from hazardous substance till the outcome. When I say outcome, till the actual physical impact damage on the target. And from pressurized disk, as I said, you can have like a gas, two-phase, and liquid. And from gas release, depending on the situation, and we will discuss what does this situation is. So this is, it could be like a fireball, it could be jet fire. And from two-phase or liquid rain, so liquid part will contribute to the liquid pool. And from two-phase and liquid, it can do flash and rain out. And once this process happens, So it called the phenomena called dispersion. So dispersion of the release happens through the atmosphere, and depending on the many factors, it could be a jet dispersion, dense dispersion, and natural dispersion. And as a result of this dispersion, so ignited dispersion may result in like a flash fire if it is in an uncongested area, or it could result in vapor cloud explosion. And obviously from liquid fire, liquid pool, if it ignites, you can have like a pool fire. So basically, you can see that in OGP flow sheet, there are from hazardous substance, depending on the leak and the condition. So you may have different scenarios like a fireball, jet fire, flash fire, vapor cloud explosion, pool fire, and even from other incidents due to external fires, you can have a phenomena called BLEVE. And this is actually the actual event happening. And in terms of the actual physical impact on the target, so these different fire may lead to thermal effect, explosion, toxic effect, and finally you will have outcome, physical outcome. When I say physical outcome, it could be a fatality, it could be injury, it could be damage to environment, it could be destruction of the building. So this kind of physical effect. So I will take you through this flow chart, basically to see certain aspect of the different release and different fire scenarios. But remember, this OGP report is always a good reference for consequence modeling. So when we talk about the release and in terms of the hazardous substance becoming like a dangerous outcome, we always start from the source term. So source term is either pressurized or unpressurized leak, and it's different discharge, which can make like a flash, rain out, evaporation, or liquid pool. So basically, the source term in consequence modeling basically define and describe you what's the rate, what's the duration, and what's the velocity of the release. So and of course, one of the important characteristic is the phase of the release. So if it's a gas, if it's a two-phase, it's a liquid. And so basically, uh, by doing like a source term modeling, so basically you get your required info to be used as an input to the consequence modeling. So basically, once you do your calculation, you identify your rate, your duration, your velocity, your phase, uh, your cloud behavior. So basically, you use all this data as an input to your consequence modeling. So it could be a dispersion modeling, it could be a fire modeling, it could be explosion modeling, and it could be like a you can be used for hand calculation or for the sophisticated computer tools available. But before doing any like a further consequence modeling, you should start with the source term. So basically to identify the characteristic of the release, behavior of the release. So in terms of the behavior, so one of the main actually important input is of course, and when I say input to the consequence modeling, and obviously the output of the source term modeling is release rate. So basically release rate, and when I say release rate, you can like imagine, so you have got like a hole on any vessel or any piping, and what does it mean in terms of the rate of that? So, and of course this rate depends on physical properties of the material. So first of all, it's really depend on the material itself. So you can imagine that releasing high pressure natural gas is totally different to the releasing of the stabilized crude oil, which is totally different to the release of the like a service water we are using at our house. So basically, first of all, this is like a physical properties of the material. And of course, second thing which rate is depends on is upstream conditions. So pressure, temperature, and phase. So you can imagine that releasing gas at 100 bar should be very different to releasing gas at which is stored at 5 bar. Yeah. And of course, the size, shape, and location of the failure is also important. So even the actual shape of the release may change the rate dramatically. And of course, so what we are trying to achieve in industry, we are trying to achieve the basically trying to achieve the release through time as we depressurize the equipment. And how we can achieve this, we can decrease the upstream pressure. So for this purpose, you will have known that you can use blowdown system, automatic blowdown system to release the upstream stem, or we limit the flows like so you can have like a, I don't know, compressor pump in upstream. So you can basically shut down this equipment, or you can use isolation and sectionalization. So basically you may have like a huge inventory throughout your site, but you can use sectionalization. You can isolate the valves with, I mean, you can isolate the vessels with the valves. So basically limit the inventory so that naturally your release rate will decrease. And the other one of the main characteristic in source term modeling is aerosol formation. And aerosol formation really kind of like a characteristic which should be considered and can change the results. I mean, your consequence modeling results dramatically, because when you do certain modeling, you make certain assumptions. For example, if the released material is heavier than air or lighter than air, but the aerosol formation can change all these assumptions. And so basically aerosol formulation is like a gas condenses due to cooling of expansion. So you can, I'm sure that you're all aware of the this process itself. So how this aerosol form. But I would like here to discuss the effect of the aerosol. So when there is a liquid droplets from your release, so it will lead to larger cloud mass, and which is really, I don't know, typically 100 times even like a more dense than like an actual vapor. And this actually changed the overall density of the cloud. So this is one of the effect of aerosol on the behavior of the consequence modeling. And evaporating aerosol can reduce the temperature below the ambient temperature, below the temperature at local to the release. So which can also change the another effect of the aerosols on the consequence modeling. And you can imagine that the colder cloud temperature may cause additional condensation even of the atmospheric moisture. And what these effects like droplets, evaporating aerosol, colder cloud eventually lead to denser cloud, and which can behave different than expected. So this is basically the effect of the aerosol. That's why, so for aerosol formation and all these kind of things, so usually nowadays like a softwares, computer softwares are preferably used for the consequence modeling. And liquid pool, so let's say if you have got liquid release, or you have got rain out, which resulted in the liquid. So basically, so here the main purpose and main mass behind basically to understand the pool size. Yeah, so you are, first of all, you need to identify your pool size so you can do further modeling on that. And in terms of the pool size, so pool basically will grow due to like a gravity, yeah, natural. So naturally it will grow until if you have got physical restoration. So for example, when you have got a storage tank, you usually put a like a band like around this. So when the pool reaches to the this physical restriction, so it cannot further expand. Or sometimes if it's an unconfined pool, it reaches the minimum thickness, so due to surface tension, and basically it cannot further extend. Or sometimes it like reaches the equilibrium. So basically, let's say you have got continuous release, and you have got also rate of material exiting the pool. It could be due to evaporation, or could be due to already burning, so it's ignited pool. So basically, when material entering to the pool equal to the material exiting the pool. So basically, pool size grow will stop. And of course, when we do consequence modeling, we are usually interested in the characteristic of the boiling pool, and the primary source of the heat is from the substrate, as you can imagine. So that's why. So there are two. This pool on the spill of the liquid behave differently on a land compared to the water. So when there is a spill on the land, on the ground, so it will the ground will cool, so which will reduce the boil off rate. But a spill on the water, so basically convection prevent the cooling. And there are certain effect of the wind and solar radiation as well. So for certain pool fire calculation, you can ignore at least solar radiation, but for certain calculation, you need to consider the effect of the wind and solar radiation as well. So when we do liquid release, so basically we do like a when I say if you are trying to, let's say, hand calculation, so basically you can do like a liquid release, like a basic orifice calculation. So it will be, so at the end of the day, you are interested in to use in the consequence modeling as an input and as an output of the source term modeling. You're really interested in the like a mass release rate. Basically, it could be, usually we do this in like a kilogram per second. And basically it really depends on the, as we described, like a area of the hole. So as you can imagine, that bigger area, bigger the release rate, and discharge coefficient. So discharge coefficient are usually different for the release of the liquid compared to the release of the gas. And this discharge coefficient sometimes is also depend on the shape and size of the hole itself. So it will be, and of course, as we discussed, upstream condition. So if you have got like a extreme upstream condition, it will result in like an extreme release rate. And density of the liquid will basically define the release rate as well. And for certain, so for pressurized, so I mean, I'm sure that you all guys know this. So basically, you should add hydrostatics head, etc. But for pressurized leak, you can ignore this because it will be a very tiny part of this. But when you are doing from like a atmospheric storage tanks, so basically you should add like a head of the pressure in the tank space. So basically you should add like a GH on the top of that, which because in atmospheric condition this hydrostatic head may change the result. And as you may know, when you do this calculation, so you identify your release rate, but you can appreciate that some of this release may evaporate due to flashing, being a flashing liquid. So basically, liquid above its normal boiling point basically will flash. Yeah, when there is a relief, and it will form a mixture of the vapor and liquid. So basically, what you can do like a flashing calculation to understand mass fraction of the released material. So and it will really depend on the heat capacity and the temperature difference between the initial temperature of the release and temperature of the atmospheric boiling point of the liquid. So due to that, so you will identify which basically mass fraction of the released liquid will flash, will evaporate, and the rest remain in the liquid pool. And for simple approach, so this is the simple approach for the using the liquid flow rate, and so I'm sure that it's also not surprised that when flashing occurs prior to discharge, let's say in the let's say we have got pipework attached to the vessel, and if flashing occurs there, so two phase will lead to reduction in the flow rate. But as an idea, at the end of the day, you are trying to understand. So let's say you did your calculation and you identified that from this scenario, your release rate will be 10 kilogram per second, and you are trying to identify which fraction of this will evaporate and which fraction of this will stay as a liquid. So out of this, if 3 will evaporate and 7 stay as a liquid. So this is at the end of the day you are interested in. And for gas or vapor release, so again, we usually do calculation to understand mass release rate. And obviously, again, it's depend on the area of the hole, upstream pressure. Discharge coefficient is usually high for the gas release, and sometimes even it's very close to 1. So which means that whatever you calculated, I mean, in liquid calculation, if you ignore the discharge coefficient, if you calculate it, let's say 10 kilogram per second, and usually it's 6 point something in reality, because there is a discharge coefficient associated with this. But if in gas calculation, if you do calculation and you identify the 10 kilogram per second, then it is usually more than 9. So it's really close to that. So this discharge coefficient is there to basically correct this factor. And of course, this again relate to the properties of the material released, like heat capacity, molecular weight of the gas, etc. So basically, it will also define the release rate. And just again, this as I said, we normally in industry use the sophisticated tools from different companies. So I will tell you a couple names available in the industry. And this formula I shared is like a for very simplified hand calculation. And you can see that here this assume like a choked flow and ideal gas without any heat transfer. But when you do computerized model, so this correction factor are there and corrected for the actual region. So let's say that you have done your hand calculation or through your software. So basically you have completed your source term and you identified that you have got some release and you know what's your release rate, what's your flash fraction, and what's your gas release. So then you will use all this output as an input to your consequence modeling. So one of them is actually dispersion modeling. So you can see we are doing dispersion modeling for the pressurized leak or from unpressurized leak evaporation part. So as I said, you did like a fraction and your calculation, you identified that certain portion of this will contribute to the cloud. So simply, we are using dispersion modeling to understand how a release will dilute in the atmosphere. So basically, you are trying to understand dilution of this hazardous or toxic cloud through the atmosphere. Yeah, and sometimes you do kind of back calculation to determine the concentration of the release material versus location and the time. So let's say you have got one hazardous stack somewhere in your flare, in your plant, in your refinery, and 400 meter away, there is a offsite public population living. Yeah, just an example, like a typical example from the cities, from let's say from Baku, which is like a even I guess could be easy for you for imagination. So let's say we have got like a oil refinery, yeah, in the middle of the city, and we have got close population living there. So let's say from at 500 meter, 400 meter. So you are doing like a back calculation to understand the concentration of the released material from this stack, from this flare header, from this discharge point. So what could be the concentration at 500 meter away from this point? So you can understand what's the effect of this on, let's say, offsite public. So basically, we use, as I said, this dispersion modeling for hazard range from toxic release, because certain materials are toxic and we cannot tolerate above certain concentration, and of course extent of the flammable clouds. So to what extent cloud would be flammable, so that if it ignited could result in flash fire or vapor cloud explosion. So in terms of the factors which can influence the dispersion behavior, so So obviously one of them and the main is the atmospheric condition. So I'm sure that you already observed this many times that one of the main thing is the wind and the wind speed and wind direction, which is defining the release direction, dilution, and extent of the cloud. Yeah, and there are also atmospheric stability, which plays a huge role on the dispersion. So stable atmosphere, natural atmosphere is very different to the unstable atmosphere. And we will discuss this. What does it mean in terms of the stability and how it affects the cloud dispersion? And of course, nature of the release as well. So if the material release under momentum, so for a certain time, it will forced by momentum. Then when it lose the momentum, it will driven by the wind. And density of the cloud, density of the formed cloud. So if it's denser than air, it will tend to go to the ground. And if it's lighter than air, it will tend to go to above and safely disperse. And as we discussed, the effect of the aerosols. So basically, uh, aerosols can presence of the droplets may change the behavior of the cloud regardless of its density. And when we say about atmospheric stability, so basically stability is like a measure of the vertical mixture. So it's not about the horizontal movement of the air, but it's more about the vertical mixture. So basically, and it really depends on the vertical temperature profile. And usually, as it depends on the vertical temperature profile, it's like a same in the same let's say latitude. So, for example, if you are here, I mean, if you are in same latitude throughout the world, you may have like a different, almost same stability, but uh, throughout the day, you may have got different stability. So basically, in stable atmosphere, so basically this atmospheric stability is marked from A to like a F, like a B, C, D, E, F. So AB is like a very unstable atmosphere. So there is a strong mixing, like when I say mixing, vertical mixing. Imagine like a column of the atmosphere on the top of you, and A and B is like a strong mixing above you. And you can imagine that if there is a strong mixing, which is good for dispersion because your cloud will disperse, will dilute quickly. But if you have like a neutral atmosphere, like a C and D, which is like a moderate mixing, there is not much uh, stability, but in the other hand, it's not too much unstable. And E and F is a very stable atmosphere, and usually there is little or no vertical mixing. So if you look at all these things, usually when we do consequence modeling, we do D and F case in our latitude. When I say in our latitude, like in UK, in Azerbaijan, in Georgia, so this latitude. So what we do in most of the Europe. So basically D is stability for the uh, moderate mixing, and usually it's represent most likely case. So basically during the day, I mean, if you look at in Baku or most of the cities in UK, so they represent most of the daytimes, and it's like a most likely condition you can have because for throughout the day, most of the time you will have D type of atmosphere, and F stability give you worst case because what we said for E and F, this is like a little and no vertical mixing. And as there is no mixing, there is little mixing. So atmosphere dilute late, and it will be more stable, and cloud will travel far away. So that's why D always represent most likely case, and F represent worst condition. And in terms of process, as you can imagine, so let's look at the through like a timeline. Yeah, so let's say in T1, in first second release happened. So what happens? So due to its momentum, due to its upstream condition, for certain, it will have like a certain momentum and it will go to the certain direction, and it will reach its maximum height it can be. And once it loses momentum, so what will happen? So it will dictate it by wind speed and wind direction, and it will start to dilute, disperse due to atmospheric condition. Yeah, and the direction of the cloud will depend on the density of the cloud. And if it has got like a certain liquid, it can rain out can happen, which can make another hazardous pool there, which is like another source of the hazards. So you can see there's a one source here. Now you formed another source there, which if it's a flammable, if you ignite this, there could be a pool fire there. And if you ignite this, there could be jet fire there. And if there is no ignition at all, eventually it will safely disperse. So with dispersion modeling, we are trying to understand extent of the disk. So where or which extent it will become safer in terms of flammability or in terms of toxicity. So basically, from mathematical model point of view, so for dispersion, we do passive dispersion. Like this is the mathematical model you can do. This is like a Gauss. I'm sure that you know Gauss from other math book. So he has got like a model for passive dispersion. So basically what model suggests you, so let's say you have got one stack or one header, then you have got release, and you can imagine like a three dimension, like a X downside, wind, Y and Z height of the. So basically, depending on wind, it will take certain direction. And what you are trying to do, you are doing like a intermittent modeling to understand what's the concentration at certain distance from the source. And as you see, as the plume moves from the downwind, so its profile will spread. So it will make, if you look at the crosswind, like a crosswind of this, it will make a bigger and bigger area. So actually, Gauss is really simplified this process in terms of the calculation. So basically, looking at the Gaussian modeling, you can calculate, you can estimate, so what's the concentration at certain distance in the plumb center line. And what you do, basically at the end of the day, so let's say you do your source modeling and you identified your release rate or release quantity. And what's the difference between rate and quantity? So basically rate is from the continuous source. So let's say you have got separator and it's leaking continuously. So basically it will be rate, let's say kilogram per second, kind of, yeah. And release quantity, if you have got like immediate release, instantaneous release, let's say you lose the integrity of the one vessel at all, so you contributed all your inventory to, so basically it's like a release quantity. And basically with this Q available, which you can calculate it from your source term modeling, you identify the concentration at certain distance. This formula may look you very like a sophisticated, but if you remember like a three dimension, yeah, this is X, Z, and Y, yeah. And here, so on this axis, so you are interested in downwind, yeah, and on that axis, Y and Y and Z value, so they are basically zero, yeah. And if you put this Z and Y values zero, so the formula will be very simplified, and you will have just like a Q, P, wind factor, and Gauss constants. And with that, you can easily calculate your concentration at certain distance from the source of the release. And of course, there are, this is like a very simplified, as I said, very simplified mathematical model to the hand calculation, but some computer softwares also use the Gauss method, passive method for calculation. But there are a number of other factors affecting dispersion, which basically cannot be addressed by the Gauss because it's like a mathematical model. So for complex model, that's why you need to certain other inputs which can change the result. So which is like a wind speed and surface roughness, as I said. So surface roughness. So if you are releasing material over the sea, over the tree, over the city, over the concrete, over the sand, these things are making difference, yeah, because surface roughness of each is different. Or averaging timing. So you can see that here we are taking any average of the certain time. Yeah, we see that, for example, after 10 seconds it's here, 20 seconds here. So if you average more, you may get different result because it's just a mathematical model. And release momentum, release density, and as we said, presence of the liquid. So because we are doing a calculation based on certain assumption, but if there is a liquid droplet, it will change the density of the cloud and it may go down. So then next, once you've done your source term modeling and once you do your dispersion modeling, so it's time to understand the ignited release effect. So it's called phenomena called fire. And as you see from our flow chart, there could be many different type of the fires. So fireball, jet fire, flash fire, pool fire, levy, etc. So then we will discuss which is which and which we should worry about this and how we can calculate each of them. So basically, I mean, this is like a simple triangle. Yeah. So if for material to burn, there should be air must be present. Yeah. In the vapor phase, and it should be like a mixed with the correct amount of the air. So I'm sure that you have heard about the upper flammable limit, lower flammable limit. So you need to be within these limits. So otherwise, I mean, if you have got just a full fuel without like air, so it cannot be burned, or vice versa. So, and if air is not premixed with the fuel, so then combustion only occurs as air is mixed. So basically, if there is no premixture, so basically it's just a continuous ongoing process actually. So fuel mix, then combustion will occur while the air is mixed after a release. And this is actually called diffusion controlled fire, and you will see what it means in terms of our like a different type of the fire. But as an idea, you can imagine that most of the fire from all these accidents, all these incidents, all these hazardous scenarios, most of them burn like a diffusion controlled fires because you are not intended making a fire. You don't want to premix the air with the fuel as they release. So fire happens as air is mixed after release. So one of them is actually flash fire. So if you see, flash fire is one of the fire which is this happen after dispersion. So if you see, so let's say this is released and it reached to a certain extent, and let's say it found ignition source somewhere here, yeah. And basically, if there is no any congestion confinement here, it will just burn it back like a poof. So it will be like fire from ignition source back to release source. So it will be just flash fire. And flash fire is just a delay between release and ignition. So basically there is a delay between the source and ignition which allowed the cloud build up. And when there's a ignition, basically flame propagate through the cloud. And it propagate through the cloud where the cloud is above the upper flammable limit. The flame will be diffusion controlled and will propagate slowly, and it will burn like a yellow smoky flame. But when the clouds within the flammable range, and the speed of the flame will be controlled by the heat transfer and kinetics. And so as for flash fire to occur, there shouldn't be any congestion confinement. So it always happen in the open area. It doesn't create any overpressure, or it creates very negligible overpressure which you can ignore. And for flash fire, I mean, you can see like if you look at, I mean, Google the flash fire, or if you can find videos on the YouTube, you will see that it's really harm is caused by direct flame contact. So if you are within this cloud, probably and most probably you will be dead. But if you are just outside the flame and even couple meters outside this fire, you will be okay because it creates negligible overpressure. So basically for flash fire, damage to be happening to the from safety point of view to the person, to the individual, you should be within the flammable zone. And of course, heat transfer is basically, I mean, all we talk about the fires and different type of the fires. So like for flash fire, pool fire, the jet fire. So heat transfer is like an important and key in this topic. So basically, I'm sure that you all know that. So the heat transfer can be transferred to a target by conduction, convection, or by radiation, which and radiation can be inside and outside the flame. And for the fire and actual damage, physical damage from all this fire, thermal radiation is the dominant mechanism. So from pool fire, from jet fire, you will see that thermal radiation is a dominant mechanism. And for this purpose, we are using actually to understand the damage, power of the fire, damage power of the fire. We do surface emissive power calculation, and it's like I'm sure that you're aware about this calculation and the rest of this weight from the Stefan Boltzmann. So basically, there is the surface emissive power is directly related to flame temperature, and it's powerful. So you can see there is a different thermal radiation models. So we use point source model. So what we do, we say that someone from X meter from the flame, and what you assume that all the radiation from this fire arises from a single point. And what you say, so this individual will receive a Q at a distance of like R. So it will be basically you will do heat release calculation. This is very simplistic model, and I don't think anyone's still using this model because it's like too conservative. So in multi-point models, this is like a more complex, more improved form of the point source model. So basically, you say that there are certain number of the point source at flame, and the individual will receive this through a different model. And surface emitter models, which is like a very famous in industry and in computer model. So what you assume, so you assume fire as a solid body, so like a cylinder, as you say. You say that all the thermal radiation is emitted from its surface. So basically, whatever surface is that, so you can calculate this through like a surface of the cylinder. And then you say that individual close to this surface, close to the source of this fire, will receive at distance, will receive certain amount of this Q. And this will be determined by view factor. So, and then of course, view factor is depends on the source and depends on the target geometry. So based on this view factor, you calculate, okay, what's your surface emission power? And out of this surface emission power, how much this individual can receive. And after that, you decide that if it's dangerous or not. So this is like as an example, view factors of cylinder. So let's say you say that someone is here. So assume that you know the and you will have known how to calculate this, the height of your fire, radius of fire. So based on all this mass, and you identify your view factor from the tables available. So let's say you say that the height, you calculate and find that height of table is height of flame is 10 meter, and you are interested if someone from someone which is at 100 meter from this flame, what it means this fire to him. So you take and you need to calculate the radius of the flame, and based on all these ratios, so let's say your distance to radius is let's say 10, and your uh, height to radius is let's say 2. So basically you cross these two figure in the table and identify what's your view factor. So let's say it's somewhere here, and you identify that it's 0.1, 2, 3, 4. So basically, whatever the surface emissive power, this individual at 100 meter will receive this amount of that. So basically, if it's 100 kilowatt per meter square, so if it is 0.04, it will just receive 4 kV per meter square. And if it is dangerous or not, it is like a further subject, so it will be a damage criteria. But this is how you can calculate actual dose received from fire using like a surface emitters models. And as I said, this is one of the most used method to calculate the heat received at a distance, at any distance. So this is an example. You can just skip this for the sake of the time. So pool fire. So this is another kind of the fire which usually happen due to liquid release or rain out when there is a pool formed and which is ignited. And pool fire is a diffusion fire burning above pool of liquid. So basically it just burn above the pool on the surface, and as air mixed through its burning, so it's diffusion fire. You can see this even from its color, it makes a lot of smoke, and vapor evaporates from the surface as pool is heated by the thermal radiation from the flame. So flame happens, and flame evaporates vapor from the surface, and the buoyancy of the hot flame entrance air is not like efficient, because and you can see that some of this and most of this fire, actually pool fires, are like a smoky. And if you give a attention, or if you like a Google some pool fires and look at its shape, it's not usually like a cylinder. It's most of the time are tilt, and this tilt is caused by like a wind. So whatever is the wind direction, so it basically tilt the pool fire. So when we do pool fire calculation, so the things are interested in terms of the source term. We are trying to identify diameter, height, of course, and this tilt angle due to wind, like a wind effect. And diameter of the pool is, again, depends on the source of release, surface feature. So it could be on the land, or it could be in the water offshore. So confinement of the spill. So there could be like a physical dike or band which will limit the further extension, or type of the fuel. So it could be a liquid or boiling liquid. This volatility will also decide the pool file diameter. And usually model used for spread of the burning pools are similar to those for evaporating pools, just a note. So these are from the same report, like a different burning rates for the different material. And so basically burning rate is really important in the pool fire calculation, because if you remember what I said early in the session, so pool fire diameter pool fire extension will stop when there is an equilibrium. So when there is a material coming to the pool will equal to the material exiting the pool. And for this purpose, you can use burning rate, because not all material burn at the same rate. For example, you can see like a gasoline, a typical gasoline you put in your car as a fuel. So there, for each meter square per second, they burn 0.05 kilogram. But on the other hand, like a butane, hexane, or for crude hexane, butane is like a almost twice higher. And LPG, LNG has got much more value, and you can see that they are even different at the on land or on water. And as we said, pool diameter will be affected by the surface characteristic. So flame height. So this is another property you need to be calculated. So you need to calculate diameter, you need to calculate height, and once you calculated diameter, so based on diameter and the burning rate, which is the characteristic of the material, you can estimate the height of the pool. So basically, the height will depend on the burning rate, then diameter of your pool. And when we say height, if you look at this pool fire, we usually refer to the visible height. So we don't have like an exact extent, but we refer to the average visible height. So this is about pool fire and jet fire. So jet fire is another diffusion fire, which resulting from ignition of the high momentum release. So there should be high momentum, which obviously should be caused by high pressure upstream. And when there is a jet fire, usually there is a stable flame from. So, I mean, you can expect this from its name. Actually, it says jet fire. So flame speed usually equals the velocity of the jet, and the rate of the air interment in a jet fire is higher than pool fire. So that's why there is a higher surface emissive power. So sometimes jet fires emit surface emissive power sometimes 2-3 times more than compared to the pool fire. And for jet fire, for hand calculation or for certain understanding, you can use correlation. So already there are some famous correlation, and which you can find this in OGP report as well. So one of them is actually from Chamberlain. So Chamberlain, and you will have known that there are certain threshold which is dangerous, like a 37.5 kV per meter square or 12.5 or 5. So for this, actually, Chamberlain basically prepared the correlation based on release rate. So you put like a release rate and you understand hazard range for that threshold. And also there are some correlation for the flame length itself. So you can put, so based on your release rate, so if you know the release rate, and you can do this by calculation by source time modeling. So basically you can estimate the length of the jet flame. So when we say length, so this visible length of the jet. And this is for hydrocarbons, and for other fuels, like there's another correlation using heat of combustion. But for hydrocarbons, we usually use 18.5 release to power 0.41. And one of the other type is fireball. So I mean, again, from its name, you can imagine the shape. So this is ball of fire. So it looks like a ball, but it's a fireball. So fireballs occurs if the flashing liquid or gas is released instantaneously and forms a fuel-rich flammable cloud. So there's like a heck amount of material released and it's ignited. So basically, there is a fuel-rich atmosphere, fuel-rich condition, which ignite. And fireball increase. So let's say it starts here. Yeah, it increased to certain radius and lifts it back to the ground. And usually, all this process actually take less than a minute, like a 30 second, 35 second, sometimes 20 seconds. But I don't think you can sustain a fireball more than a minute. And most common mechanism for fireball formation actually is a Blavi, the phenomena called Blavi. So if you have got like an external fire around your vessel, is this boiling liquid expanding vapor explosion. So what will happen? So this external fire can reach to the fuel which flammable, and this you will add all this material to the ignited atmosphere, and this will result in boiling liquid expanding vapor explosion. Just a second. So yeah, this is like a kind of mechanism. So let's say you have got like a vessel, and you have like external fire, and obviously and it will rupture, and you will add all material into your cloud, and it will result in blaze. And if you remember this like a definition actually, so boiling liquid expanding vapor explosion. So maybe question. So what do you think? Can blaze occur following, let's say, LPG? Any idea? Let's say if this material LPG. So any thought? So again, remember the definition: boiling liquid expanding vapor explosion. So what happens when this happens? So this material should boil. And what do you think for LPG? If you have got LPG here, if you have got propane butane, can it lead to blaze? Any thought? Yeah, you can just put your answer in the chat, or you can just like come out of mute and share your idea. I hope I am not talking to myself. So there is actually one simple rule here. So at this condition, at this atmospheric condition, this material should boil, and that's it. So if it is boiling liquid, so if you remember the name, boiling liquid expanding vapor explosion. So for example, what's the boiling point of the LPG? It is well below the normal ambient condition, yeah? So when you have got LPG release, it will immediately boil, and you will add all this vapor expansion into the cloud, and it will result in blaze kind of this, yeah? Okay, so fireball correlation. So in terms of certain correlation, so diameter of the fireball will again depend on the fireball mass, and there is some correlation. And duration, as I said, again, mass in the fireball, but you can imagine that it will take seconds, not minutes. So height of the fireball, so it's usually a fraction of the diameter. And surface emissive power, so using all this input, so you can calculate the surface emissive power. And once you calculate your surface emissive power, and if you remember our V factor calculation, so based on that, you can calculate what will be radiation received. Let's see if someone 100 meters away from this. So you can use your surface emissive power, V factor, and time exposed. So based on that, you can understand what can be the radiation received at that point. And then based on damage criteria, which is like a further subject, and I don't think we will have time actually to touch on this today. So based on damage criteria, you can decide if the radiation received is dangerous for person or building or the other process equipment or not. Okay, so we just quickly touched on the fireball, jet fire, flash fire, pull fire, or even blaze. And one of the other mechanism actually is vapor cloud explosion. So explosion is, so as I said, release dispersion of the cloud which if ignited can result in either flash fire or vapor cloud explosion. And this either or is really depends on if the area is congested or not, or confined or not. So simple thing, for example, if you have got natural gas, normal like a domestic gas we are using, if you release this outside, it will just disperse. But if you release this inside your home, due to confinement from the wall, it will make, if you ignite this, it will make overpressure wave. So this kind of things decide if it will be a flash fire or vapor cloud explosion. And just bear in mind that vapor cloud explosion, offshore vapor cloud explosion and characteristics offshore vapor cloud explosion, and I will let you know what does it mean. So what decides if it will be flash, just a flash fire, just a poof of fire, or explosion? So this is two phenomena. First one is called confinement, and the confinement is the presence of the surface which significantly prevent or limit combustion of the product. As I said, your home, you have got walls everywhere, and yeah, sorry guys. So basically confinement, so presence of the wall, like in your house. Yeah? If you have got like an indoor domestic gas leak, and if there is ignition, it will result in explosion because there is a wall. Uh, I see someone raised his hands. Yeah, Emmanuel, go ahead. Is there a question? Emmanuel, if you are saying something, you are in mute. I cannot hear.
Emmanuel, if you would like, you may write your question in the chat box, or you may just unmute and chime in. Maybe by mistake, probably.
Okay, I will continue. Yeah. So basically, these walls which prevent or limit combustion product expansion that result in the overpressure or congestion. So sometimes you don't just need like a walls, floors, plate decks, but the actual equipment itself. So there could be like a pipe racks, compressor, pumps, valves, etc. So this, I'll come back in a second. Sorry guys, someone in the door. Sorry guys for that. So yeah, basically this is like a presence of the obstacles, and as I said, the obstacle can be like a pump, compressor, valve, pipe rack, anything which generate turbulence when there is a gas there, vapor there, flammable mixture there, which act to accelerate flame speeds, and this acceleration create overpressure and explosion. So example of the congestion. So this is like a happened maybe now 15 years ago in BP Texas refinery. So there is a overflow of the one of the atmospheric stacks, which due to congestion here, like a process facilities, there is a distillation column, there is a pipe rack, etc., which resulted in like overpressure, and this explosion killed 15 people. And another unique example from Ufa, Russia. So actually, so trees in the forest actually acted as a like a congestion. So gas cloud drifted for a distance of couple miles, and trees flattened like a with a blast. So basically, when they are saying that the explosion equivalent of 10,000 kilogram of TNT, but you cannot explain this with the congestion of this congestion effect of these trees, which actually results in 600 fatalities. And another phenomenon in explosion. So basically, first there should be confinement or congestion to explosion to happen, and the second, deflagration or detonation will decide the extent, the power, the damage of the explosion. So when explosion with resulting a flame moving at a speed or less than of the speed of the sound, so and this called deflagration, and this typically creates less than 3 bar G overpressure. And when detonation happens, so obviously it's moving speed greater than the speed of the sound, and this pressure sometimes rise 10 times of the deflagration. So it could be I don't know, 15-20 bar of the overpressure. And you can see that, so due to this effect, actually moving speed, so entire gas cloud actually is contributing to the blast generation. So whatever flammable material you have got in the cloud, it results in the overpressure. Then typical vapor cloud explosion models. So we use two different type of the models, like empirical models and numerical models. So for empirical models represent the flame acceleration, and this is really appropriate for the far field. So that's why when you do onshore modeling, because in onshore you have got like a more footprint, and you are not interested in what will happen in 2 meters, 5 meters, 10 meters. You are more interested in what will happen in far field. So we do empirical. We can do actually empirical models. So there are certain examples. So TNO models, CAM model, BST model. So one of them, for example, TNO is like a widely used for doing onshore explosion modeling in specifically in oil and gas industry. And there is also some numerical models, which is solution to the differential equation. And so basically you they define the gas cloud, they divide gas cloud into the individual cells, individual mesh, and that's why it's really appropriate for the near field modeling. So like when you do offshore modeling, and one of the famous software is Flex from Gexcon company in the UK. So they are doing like this numerical, this individual cell models, which is very appropriate for the near field. So it will show you the effect of the overpressure in couple meters. So you can understand what kind of overpressure you will see in near field in, let's say, in offshore platform. And in this numerical model, it includes all the important factors that can affect the vapor cloud explosion. So the one of the oldest model I would say is TNT equivalent model. So basically what we used to do maybe many years ago now. So we do, so basically the assumption is that explosion power of the gas can be related to the equivalent of the mass of the TNT. So basically what you say, so you say that this is the amount of flammable gas I have got, and this is the amount of the X kilogram of the TNT, and you take the hazard contours of the TNT explosion. So this is very simple model and not basically represent the actual situation, because as you can imagine, it cannot take into account the flame acceleration mechanism we discussed, like this deflagration, detonation, confinement, congestion. It's just a simple conversion of the gas cloud explosion to the equivalent TNT amount available. TNO multi-energy model. So as I said, it's one of the empirical model, which is widely used for specific, especially for onshore models. So what what are the main assumptions are actually. So the main assumption is only congested portion of the cloud, not the entire volume, contribute to the blast effect. So basically, uh, you assume hemispherical and homogeneous and stoichiometric cloud, and then you say that ignition and explosion happens in the center of the obstacle, and then based on that, you say what's the effect of the explosion. And different curves represent the good thing with TNT model is that if you look at the TNT charts, so you can see that for different congestion, so there are different charts. So you can see it has got from 1 to 10, and for these are the strength index, so from 1 to 10. So every index actually indicate different strength. For example, 7 indicates the explosion pressure 1 bar G inside the congested combined volume. So this is the curve. So basically what you do combustion energy scale distance calculation. So based on that, so this is like an example. So basically you do calculation to so let's say you are interested in what will be the explosion power and what will be the effect at 100 meter from the source. You do combustion energy scale this distance, and based on this distance you find your charge radius, and you find and based on your charge radius, so based on your congestion, so let's say you are on this column, and if your charge radius just the same, if result in 10, so you mm, look at this chart and say that okay, it will result in 0.02 bar G over pressure. Then you will further interpret what does this overpressure do to the people, to the building, to the structure, etc. So this is about Tiana blast chart, and as I said, it's like a widely used for onshore explosion modeling. So this is like an exercise. I think you can just skip this for the sake of the time. So there is also, if you look at the chart, there are also some other explosions which is not from the pressurized or unpressurized leaked, but they are from the other incidents, like from condensed phase, runaway reaction, dust, physical effect, etc. So you can see these are the different picture from the different event. So you can see here the actual missile of the vessel, so which is not like about hydrocarbon itself, cloud itself, but the actual missile of the vessel. So one of them is actually vessel rupture, as you see this in example. So when vessel rupture, the one obvious case is like this radiation, thermal radiation, overpressure, blast, etc. But the other thing is that you will have flying missiles from the vessel itself. So for this kind of things, what we do like we do so if a vessel is overpressurized, we say that it may be ruptured. And for this, we do like a for sphere or for cylinder, we do different calculation, and we understand what the resultant release of the energy can, if the resultant release of the energy can generate a blast wave or missile fragments. And then we try to understand the effect of this missile fragment to the neighbor facilities, to the people. So simple approach. So this is again a simple approach. So what we do calculation of the energy released. So you can use like you will see this in the as a reference. So you can use like a broad equation, and then based on this, so when you calculate the energy released, you convert this equivalent mass of TNT and basically use the TNT curve to determine overpressure of the distance. So you can see this is like a kind of missile assessment. So this is like a source of the release, and you can see this red dot are the missiles can be found from. And for missile, just bear in mind that we usually do like a probabilistic. So they are like a just model probabilistically based on number of fragment and travel distance. So it's not like a sophisticated science. So it's just a probabilistic calculation. Because some company decide to do this because the missile also can accompany explosion. So when fragments from this integrated pressure vessel fly away, so it could hit to another vessel and result in the escalation. That's why some company decide to do probabilistic missile calculation as well. Okay, so the next topic actually is, actually it's not next topic, but this is like a continuation of the consequence modeling. So once you, let's say, do all this calculation, all these nice things, and you identified what's the size of your thermal radiation, what's the size of your pool fire, jet fire, flash fire, dispersion result. So the question is, so what? So how it will affect us as a person, or how it will affect environmental, asset, reputation. But before moving to the, I will spend I will go through damage criteria very quickly for the sake of the time. But before that, I will just like to pause and to see if any questions so far. Okay, I accept silence as we are doing well. And I will do a very quick overview of maybe in 5 to 10 minutes the damage criteria. So as you see, we moved from hazardous substance. We identified what's our pressure leak, unpressurized leak, other incidents, like a source term modeling, like a discharge rate, etc. Then flush, evaporation, then dispersion calculation, to understand what will be the extent of the cloud. Then different fire models, like a fireball, jet fire, flash fire, what we call explosion, pull fire, levy. But the main question is, what's the outcome? So what will be the effect of that? So is that toxic effect, thermal effect, explosion, fragment effect is dangerous, acceptable, or not? So if you look at all these four different, actually, including missiles effect, so we discussed about thermal, overpressure, toxic, and missiles. So you can agree that all of them can be dangerous to people. So thermal, overpressure, toxic missile could kill someone. Toxic may be damageful for environmental. Thermal, overpressure, and missile can damage the asset, like your second tank, your second pump, your control room, etc. And all of them will definitely damage your reputation, your company reputation. So this is the last thing you would like to have, being on the a main news saying that there is a fire in the refinery of the X company. So in terms of the estimation of harm, so we use for doing specifically for thermal, toxic, and overpressure, we do based on dose. When I say dose, it's based on quantum and based on duration, and we determine the harmful dose and use probabilistic equation to understand what could be the lethality rate. So for example, so this is like a use of probit for people, let's say. So it's like a function of, it's like a probit value with two constant and logarithmic function of the dose. So basically this value will result in range of from 2 to 8, which equivalent of 1 to 99% fatality. So when you do calculation, so when you do all your a source term consequence modeling, and when you have got outcome, you put this function of dose received to your formula, your probit formula, and to understand what will be the physical outcome. Yeah, for example, if you do this calculation and you identified that this y value is 9, which means that obviously anyone is there will be dead. So if there's a 10 people, the 10 will be dead. And if this value is less than 2.67, if result in 1.98, which means that you are there is almost no chance of the fatality. So basically for outcome, we use like a dose-based probit equation. So for example, this is like one of the example. So let's say you calculated, you put your a function into your formula and calculate and found that this is, I don't know, let's say 5.99, yeah, and then you come to the table 5.99, and you see that is equivalent to 4%, which means that if there is 100 people in this area, 84 would be dead. And in terms of the using of this function, this probit value, so as I said, K1 and K2 are the constant, but for function of the we for different outcome, we use different function. For example, for thermal radiation, we use thermal dose power to 4 divided by 3 times time. So time is usually in second. So basically you say this is the thermal dose you received. So you do, let's say, your this pool fire calculation and identify that what's the based on your emissive power, based on your view factor. This is the X amount of kV per meter square you will see, and you will expose this 30 seconds. And you calculate this, and you find your V, and based on constants, and each famous people has got different constants. I will show you this quickly as well. Then based on this constant, you find your Y, and you put this Y into your table to understand the extent of the damage. So these are the different like thermal radiation factors. So I don't know if you ever heard about the Lee. So Lee is kind of one of the founder for, let's say, process safety. So he has got loss prevention book, and in his book he's giving about this K1 and K2 factors, and also Eisenberg has got different value, but they're always matching to each other. So you can use one of these to understand the extent of the things. So this is for thermal radiation, but so basically thermal radiation, function of the thermal dose and the time. And for toxic substance, this is again function of the concentration. So usually in ppm, and how much time you will be exposed this in terms of minutes. And N actually depends on the hazardous material, because not all hazardous material are equally toxic. So that's why they have got different M value. And as an example, for example, for ammonium and chlorine, N is 2, but for H2S, ammonium N is 1.4. And then this is the K1 and K2 constant values from again Lee. So basically you can put these values here, and once do your dispersion calculation, Gaussian model, let's say you identify that what's your concentration in ppm, then based on this calculation, you understand if those people subject to this toxic release, how many of them could be dead. And for our pressure, there is only one value as of like a blast over pressure. So which is a P, is like a peak over pressure, and function of the let's say bar G, and it's another like a K values as an example from again I think Lee. So basically again you do the same calculation, you do lower overpression calculation using TNT, TNO, etc. One of the model, and when you know your peak over pressure rate, you put this into the formula and identify what's the probit value. And based on probit value, you can decide that if there is 10 people, 5 of them could be dead. Again, as I said, this is like a probabilistic value. And you may have asked, okay, what does this thermal radiation means? Like for example, I did calculation and I showed see that one of them is like a 25 kV, but the other is 5 kV. So what does it mean? So this is like from UK HSE, so approximation of the human vulnerability. So you can see that 1.2 is like a usual actually sun thermal radiation you receive from the sun in the summertime. And if you have got above 35, it's really dangerous, and it could be significant chance of the fatality instantaneously within the seconds. So for toxicity, I will not go to details for the sake of the time. I'm planning to finish the session in 2 minutes. So we use like a slot and slot values, so like a specific level of toxicity or significant likelihood of death, which means that typically 50% fatality. So we use this value to identify the toxicity. And again, each toxic value has got different slot and slot values and different n values. So based on that, then you can calculate slot and slot. And for overpressure impact, if you see like a 3 bar overpressure, there is a 95% chance of the fatality. But if you see like a 2.5 psig, there is a 1% of fatality. So this is the kind of just idea what it could be in terms of the overpressure. And missiles, so I will not go for the okay, maybe quickly. So I will not go for the missiles. So, but again, you can imagine that the estimation of the harm, again, number of the missiles, direction, distance, and momentum. So basically, based on the overpressure, impact velocity, and impulse. So you decide what's the chance of the injury, what's the chance of the fatality. For example, based if you have impact velocity is more than 90 meters per second, so there is a serious wound near to the 100% probability. And there's also equivalent damage criteria for the environment as well. So there is a Matte threshold which says that death or serious sublethal of the 1% of the common species or the 5% of the ground cover, and so is a specific like a environmental index, and based on this index, if this index is more than 100, so which means that it's like there's a significant risk to the environment. I would like to stop here and see if any question. If not, I think we can close the session here.
Gerald, do you have any questions to ask?
So if no question, I think we can close the session.
Yes.
And thanks for joining. Yeah, back to you, Rashad.
Yes, I believe we can close the session. I would like to thank you for your presentation. Honestly, I believe this topic is, and all information that you have shared with us is something new to most of us. For me, honestly, some part of it, some considerable portion of it was new for me, and I believe this is the same for most partakers. And thank you for sharing your knowledge. I believe we will meet next week again. So see you there as well.
Yeah, bye for now and have a nice weekend and talk to next week.
You too. Thanks a lot. Thanks all for joining. Tomorrow we'll be meeting with you in our two next sessions. Thanks all. Bye.